MECH2410 Engineering Materials Tutorial 8 Phase Diagram and Phase Transformations. Tutorial 8 Part 1 Basic Terms, Phase Diagrams, Isomorphous Alloys. Phase diagrams are very important and very useful when we try to study the properties of alloys. It is because the microstructure of alloys and its mechanical properties are strongly related. And the development of microstructure of an alloy is related to the change of the composition of the phases of the alloy and therefore characteristics of its phase diagram. In addition, phase diagrams provide valuable information about melting, casting, crystallization, and other phenomena of phase change of the particular alloy. In this tutorial, I will introduce a lot of new concepts, so there will be a lot of wordings. Some basic definition of some special terms. Phases. Phases is a homogeneous portion of a system that have uniform physical and chemical characteristics. For example, for an oil-water mixture, it contains two states. One is the oil state, and one is the water state. As we know that oil cannot dissolve into water, but however, for salt water, there is only one state, that is salt water itself. As salt can dissolve in water completely. Components. It is the chemical species, elements and compounds that the particular alloy contains. System. System could refer to a specific body of material under consideration. For example, a ladle of molten steel, or it may relate to the series of possible alloys consisting of the same components, but without regard to alloy composition. For example, the iron-carbon system. Phase equilibrium is the characteristics of the system do not change with time, but persist indefinitely under invariant state variables. What is state variables? State variable describe the thermodynamic system. For example, a system's composition, a system's temperature, and a system pressure, for example. And if the state variable doesn't change for a system in phase equilibrium, the characteristic of the system will not change with time. Let's have a look at the picture here. G is the free energy, which I have the following definition. At minimum free energy, they will attain its phase equilibrium. The X is various state variable, and one can varying those state variable to let the system attain its phase equilibrium. Metastable state. In this picture, the metastable state is shown here, and often in solid system, a state of equilibrium is never completely achieved because the rate of approaching to equilibrium is extremely slow under metastable state. For example, diamond is a metastable state of carbon, but graphite is the true equilibrium state of carbon. But we know that for diamond to be transformed to graphite, it requires a lot of time and a lot of activation energy. So the time required for transformation is quite large. And I represent it in this picture. For a system in this point, they need a lot of energy, activation energy, to approach to its phase equilibrium. Therefore, we consider this point as one of its metastable states. The first concept which is using to describe the phase change phenomena is solubility. And as you remember that solubility is the amount of solutes that can be dissolved in solvents under certain temperature and pressure, which is an important concept in alloy, as alloys are basically solid solutions. Many engineering questions are related to solubility. For example, how much zinc can be put into copper to make brass, which is a zinc and copper alloy? And we can use phase diagrams to serve for our purpose. In this tutorial, I will introduce phase diagrams in these slides. This phase diagram here is describing the salt water system. Basically, it describes for varying composition and varying temperature, what will be the phase composition of the salt water system. At the red line here, it is the solubility limit. It is because when you pass through this line, some of the salt will not dissolve into the liquid, as marked in this region. You can see that it contains two components. One is salt, solid state salt, and the other component is the liquid, which is the brine and salt water. At this part, it is completely liquid, and at this part, this is partially pure ice and partially pure liquid. Pure brine, not pure liquid. And you can vary the temperature and have different composition of phases by looking in this graph. And that's why such phase diagram is very, very important in the description of the phase change phenomena. For alloys, it have similar phase change diagram for the different kind of alloys, which I'm introduced in later slides. Phase diagrams. As I just mentioned, we can describe complex phase changes by phase diagrams, and phase diagrams are constructed with combinations of three state variables: temperature, pressure, and composition, and they are plotted against one another. For unary phase diagram, it describes system with only one component. For binary phase diagrams, it describes system with two components. If the system with two components are isomorphous, that means the two components have complete liquid and solid solubility and or same crystal structure. One example of isomorphous system is copper nickel alloy. And the phase diagram here describes such system. At from 0 to 100 weight% nickel, you can see that there is no pure copper or pure nickel phases in both liquid region and solid region. And there are actually many special terms of phase diagrams. I will use the previous phase diagram, which describes the copper nickel system, to introduce to you. The first thing is the 80% nickel. 80% nickel stands for atomic percent nickel, which is the fraction of number of nickel atom versus number of total atom. atomic percent nickel is here. Weight percent nickel. Weight percent nickel stands for fraction of weight of nickel within the alloy versus the total weight of alloy. So be careful, they are different. Atomic one and the weight percent one are different. One describes the number fraction, and another one describes the weight fraction. And there are two lines, liquidus line and solidus line. Liquidus line, basically, when you move beyond this line, all of the component of the alloy becomes liquid. Beyond this liquidus line. Oh, basically this line, my drawing is terrible, but you can see that when you move beyond here, all of them becomes liquid. Nothing here is solid. Solidus line, the line here. My drawing is also terrible. Sorry about that. When you move here, the region here are completely solid, and it is denoted by alpha. Alpha stands for the homogeneous solid solution of nickel and copper, and you can see that there is no liquid state in this region, alpha region, and that's what liquidus and solidus lines stand for. Interpretation of phase diagram. Example. Okay, the first thing I would like to discuss is how can we determine the phase present at a specific temperature and composition, etc. And basically, we just need to locate the desired temperature and composition point of the diagram, and just note down the phases with which the corresponding phase field is labeled. For example, I would like to find at 1300 degrees Celsius and at 50% weight percent nickel, phase exists at equilibrium for such copper nickel system. And answer is, we draw two lines here. One indicates the temperature, 1300 degrees Celsius, and one indicates the composition, weight percent nickel. Be careful because he asks weight percent and draws up, and the point where they meet is our desired point, and we can see that it is located at the region which contains two states. L stands for liquid. Alpha is the alpha phase, and from this picture or from this diagram, we know that it must be the homogeneous solid state for this copper nickel system. And why I will need to highlight at equilibrium is because phase diagram do not consider time effects, and it only consider the phase composition of a particular system at the equilibrium state. The time effect of the phase change will be discussed in later parts of this tutorial. Second question is, identify the composition of each phases at a specified point. The first thing is, we still need to identify the phase present at that specified point. And the method I've described in the last slide. For one phase case, at that specified point, that means at that point, the alloy contains only one phases, and that phases must be 100% of that alloy, and that means the chemical composition of the only one phase is similarly equal to the overall chemical composition of the alloy, which is quite trivial and quite straightforward. But for two-phase cases, there is some specified step you need to do to find the composition of each phases at that specified point. The first thing is we need to draw a tie line construct across the two-phase region at the temperature of the alloy. 2. The intersection of the tie line and the phase boundaries on either sides are noted. And third, perpendicular lines are dropped from these intersections to the horizontal composition axis from which the composition of each of the respective phases is read. For example, at temperature 100 degrees Celsius, 50 weight percent nickel, what is composition in weight percent of each phases exists at equilibrium? So let's use the phase diagram. At this phase diagram here, we first find line or find the point which is located at the alpha phase plus liquid phase region. So therefore, there is two phases present at that specified point, and we want to find the chemical composition of both of each phases. One phase is alpha phase, and another phase is liquid phase. So let's zoom in the picture, and here is the zoomed in picture. The tie line is constructed by drawing a line here. This one is straight line due to my terrible hand drawing skills, and the blue lines marked the region or the point where the tie line intersect with the liquidus line, and we draw a vertical line to find the composition reading. And by the similar way, the yellow line here indicates the solidus line, the intersection between the solidus line and the tie line, and we also find the reading here. Okay, so you may want to ask, there is no readings. There is only three these readings here. How can we read the readings for this red perpendicular line? We use a ruler, and remember to use a ruler. This is very, very important. In exam, do bring a ruler for all these readings, phase diagram readings. And the answer from previous slide is liquid is 46 weight percent nickel and 54 weight percent copper. That means for the liquid phase at this specified point, it contains the chemical species, two chemical species at the following composition. For alpha phase, which is the solid phase, it contains 58% weight percent nickel and 42 weight percent copper. And that means for liquid phase, we take the readings at the intersection between the tie line and the liquidus line. For solid phase, for the solid alpha phase, we take the readings of the intersection between the solidus line and the tie line. The third question is amount of phases present at the specified point. If the specified point only contains one single phase or one phase only, then the answer is pretty trivial. There is only one phases there. If there contains two phases, we use the lever rule. And with similar methods, the first thing we still need to construct a horizontal tie line, which across the two-phase region at the temperature of that oil alloy. The overall alloy composition is located on the tie line. The fraction of one phase is computed by taking the length of tie line from the overall alloy composition to the phase boundary for the other phase and divide by the total tie line length. We will use an example to illustrate the lever rule, as it is quite difficult for you to understand using the word. Okay, just for example 2, what is the phase fraction of our phase and liquid phase? So the specified point is still the point we use for example 1 and example 2. So let's go to the next slide. Similar steps mentioned for example 2 in terms of the construction of the tie line. We construct the tie line as described here, which contains a white, red part and a blue part. We then, construct two perpendicular lines, which mark the intersections between the liquidus line and the tie line, and between the solidus line and the tie line. Again, we take the readings. We first take the length, total length of this tie line first. Again, as I mentioned, do use ruler. It is very, very important. Second, we take the length readings of the red part and blue part. And the lever rule that's specified. For the liquid state, the liquid region is here. This is a liquid region. Therefore, weight percent of liquid by lever rule is the blue part. Remember, it's blue part, not the red part, over the total length, which is the green part. And this is the weight fraction of the liquid state at that position. For alpha phase, and it is the red fraction or the red line length over the green line length, not the blue one, but the red one. It is because the solid alpha phase is at here. It's at the right hand side of this tie line. Therefore, it is not the blue part, but the red part. And the answer is here. And if you want to find the atomic percent of this of example 3, and you just use the atomic percent composition readings, which is at the top upper part of this phase diagram, but this is not shown here. This is only the zoom in part of that phase diagram. And just follow the same procedure and use the same principle of the lever rule, you can still get the answer. And just like I have just mentioned, lever rule can also be used on calculate atomic percent, which counts on the number of atoms for those phases. And just make sure you use the atomic scales on the phase diagram. Microstructure development of isomorphous alloys. Isomorphous alloys, I repeat the definition, which means that two components of that alloys have complete solubility in each other. So there is a weight and grain structure relation when it solidifies at different compositions. Let's say for these two pictures, one describes an isomorphous system with slow rate of cooling, and another thing described an isomorphous alloy with fast rate of cooling. For very slow rate of cooling, the growth of the grains is slow and that means the composition of grains formed at different point in time is uniform. And as shown here, it is uniform, and it is indicated by the readings here, which is 35 at this case. The final solid, entire solid, at any point of this fully solidified solid, they have the same composition of nickel with respect to that, but at liquid state. But however, at fast rates of cooling, it will not form a uniform solid, but it is more likely to be a onion structure with different concentration or different compositions, chemical composition at different points of this solid. It is because, using the lever root argument, we should know that at different points of these solids, some solids, but with, according to this graph here, at this line, there should be some of the alpha phase solid with 46% nickel. How can we know that it is 46% nickel? You draw a line here. We mark 46% nickel. With 46% nickel, we will first solidify based on the lever rule argument. And when we go down with the temperature, let's say here is the line. You draw a line going down here. It is 42% nickel. And using a similar argument, we will form an onion-shaped or a solid with onion-like composition. At different points, they have different chemical composition for a single alloy. And that's why actually the time rate for phase change is also very important when we discuss about the phase change phenomena within an alloy. And for that, we will discuss in later slides. Here, I just use an introduction and how you interpret the phase diagram in these purposes.